reinforced with particle and fibers. I put also fibers over there to compare, yeah, a little bit some, let's say, properties. But the experimental results that I will present will be focused only on particles. Okay? So we'll see some technologies for composite material reinforced with particle. Some, let's say, theory concerning the gas to liquid transfer of the reinforcing particle. Another one, experimental results concerning the gas to liquid and liquid to solid transfer of the reinforcing particle, and property of the composite material reinforced with silicon carbide particles. So let's see a little bit only two advantages of composite material reinforced with particles. Low cost compared with fibers. Simple reinforcement technologies. Kalpak asked me 2 days ago, yeah, if there is a possibility, yeah, when I talk about some particles inside of the polymeric, to mix, okay, to mix the particles. You will see later that we got together, doesn't matter if I'm the first author, let's say, and patent in Romania, yeah, for this, let's say, type of equipment, yeah, in order to mix the particle inside. But the base method, as you already know, is the vortex, okay, method. So there are a great, of course, you can see variety of the particle used in obtaining the reinforcement of composite, such as particle in form of metal oxide. And you can see aluminum oxide, silicon oxide, titanium oxide, magnesium oxide, and so on. Carbide particles from silicon carbide, titanium carbide, metal particles in form of steel shot and cast iron, carbon graphite or amorphous carbon graphite particles. I put over there, in case of aluminum alloys, as matrix used, yeah, which are the particles, you can see here, which are the average diameters and which is, let's say, the proportion of the dispersed material. I mean, how many percent, yeah, of the material is dispersed. So you can see the highest, let's say, on graphite, but take into account the proportion of dispersed material, yeah, around, you can see aluminum oxide, yeah. I mean, one of the most, let's say, used particle as for reinforcement. A little bit, comment. In case of particle reinforced composite material, the mechanical property change is less than in case of the fiber reinforcement. We already know, I think, this, let's say, property was mentioned many times during this week here. So the mechanical properties will decrease, okay? These materials are significantly improved tribological properties, don't forget about that, resistance to air and shock amortization, so we increase. Concerning the fiber characteristics, we can talk about the stiffness, density, hardness, thermal coefficient of expansion, specific resistance to breakage, and so on. The fiber, yeah, has, let's say, the main, rule in order to make a general classification. I mean the ratio between the length and diameter. If this ratio is bigger than 1000, we can call the continuous fiber, yeah? In case that the ratio is between 300 and 1000, we can call long discontinuous fiber. And if the ratio between length and diameter is 10, we can call it short discontinuous fiber. Discontinuous short fiber have high levels of resistance to breakage. The best properties are obtained for carbon fibers, yeah, many times during the lectures, during this week, yeah, we talk about carbon fibers. Boron fibers, monofilament, and the very short, you know, whiskers of silicon carbide. From the fibers from ceramic material versus metal one have a low thermal expansion coefficient, I mean high dimensional stability and higher hardness. But of course, because we are talking about the ceramic. So, why we use fiber reinforcement as a thin with a thin diameter? As the diameter decreases, the inherent flows in the material also decreases and the strength increases. For better load transfer from matrix to fiber, yeah, because as you remember at the very beginning, when I mentioned which are the main, let's say, goals of the matrix and which are the main goals of the fiber, yeah, the composite require larger surface area of the fiber matrix interface. The fibers should be flexible so that they can be bending easily without breaking. Okay, that's why, let's say, we got a little bit answer, yeah, about the questions. I put also here some, let's say, shape of the fibers, yeah, I mean circular one, and we can put here, we can call, you can put the name glass one, carbon, organic fibers, alumina, silicon carbide, elliptical shape, alumina, mullite, triangular shape, seal, silicon carbide, whiskers, and of course another, you can see hexagonal one, rounded triangular one, kidney bean in case of carbon, and trilobal, you can see shape in case of carbon and iron. So the main shapes of the particle that we can use, yeah, we can use inside of composite material as reinforcement. Also, if you want to make an idea about the natural fibers, yeah, because some of your colleagues are involved in natural fibers, yeah, we can split it, let's say, on animal fibers, vegetable fibers, and mineral fibers. Yeah, and I put here some example: silk, wood, spider silk, sinew, camel hair. Another vegetal fiber: cotton, jute, bamboo, and so on. Hemp, banana, yeah, and another one. Which is the natural fiber that you are working? How? Okay, okay. So the mineral fibers: asbestos, basalt, mineral wool, yeah, glass wool, and so on. And of course, I think we can carry on, yeah, with the other, yeah, example on the first, second, and the third, let's say, types of the natural fibers. Let's see a little bit comments about glass and quartz fibers. Produced by extruding molten glass at 1200 Celsius. Passed through spinnerets of 1 up to 2 millimeters as a diameter. Then drawing the filaments to the produced fiber of diameter between 1 up to 5 millimeters. And individual filament is small in diameter, isotropic in behavior, and very flexible. And you can see here about the glass fiber, yeah, the types, the main type of types of the glass fiber. I mean E-glass, yeah, with the high strength and high resistivity. S-glass, high strength, modulus, stability under the extreme temperature corrosive environment. Yeah, it's important to point out. R-glass, enhanced mechanical properties. C-glass, resists corrosion in an acid environment. And D-glass with dielectric properties. Also, the glass fiber and quartz fiber are obtained in a high purity quartz crystals. Okay, 99.99%. They have lower density and higher mechanical property than glass fiber. So, it makes more suitable on the largest, let's say, industry as aerospace industry. Okay? Quartz fibers have a number of features such as high resistance to chemical agent activity, resistance high radiation, high hardness, and dimensional stability. This is only the general, let's say, image sketch about the glass and quartz fibers. Carbon fibers. Different fibers have different morphology, origin, size, and shape. Normal one. The morphology is very dependent to the manufacturing also process that we choose. The size of individual filament range between 3 up to 14 micrometers, hence very flexible. The maximal temperature of use of the fibers ranges between 250 up to 1000 Celsius. The properties change, of course, with the temperature, range of the temperature. And I put here some information about the carbon fibers, which is the equipment that allows to obtain the carbon fibers. Please take into account that we need 2 stages, first and second step. In the first stage, the liquid raw material, you can see, number 1, is subjected to gasification between 300 450 in the combustion chamber number 2 under an inert gas atmosphere. Afterwards, the raw material gas number 3 from this one is led into the mixture chamber number 4 with the inert gas, look, from the enclosure number 5 and the active gas from the enclosure number 6. The mixture afterwards is led gasification furnace reactive number 7, where at temperature around, let's say, between 700 to 1200 thermal decomposition occurs of the raw material. The carbon cores are deposited on the substrate number 8. And on the second step, the carbon fiber is heated between 1 up to 10 minutes in a furnace with an inert gas atmosphere, and look the temperature, 2700, 3000, thus resulting the complete graphitization of the fiber with a degree of orientation around 99%. So it's a general also sketch, how we can get the carbon fibers. Of course, if you are looking, if you try to find on internet, of course you can find the details, of all technology, including also the technological parameters.
And is the raw material petrochemical?
How?
The raw material for carbon fiber. Is it
Could be.
Could
be. Organic fibers. Aromatic polyamide family of nylons. Polyamide 6, nylon 6. Polyamide 6.6, nylon 6.6. The diameter of filament about 12 micrometer and partially flexible, but with high tensile strength. Very low elongation up to the breaking point, and significantly lower strength in compression. Boron, ceramic fibers. You can see the boron, it was the first advanced fiber developed for structural application. Look at the year, 1959. Okay, so many years ago. Manufacturing by CVD, we already present what means CVD process, chemical evaporation, deposit. Fiber diameter range between 33 and 400 micrometers, and typical diameter is around 140 micrometers. Boron is the brittles, hence large diameter results in lower flexibility, strong in both tension and compression, high cost of production, in case of boron fibers. Alumina, Fibers retain strength at high temperature, and silicon carbide, you can see that the filament is similar to the carbon fiber. I mean, take into account the size, yeah? Size around 14 micrometers and more flexible. Silicon carbide shows high structural stability and strength, retention even at temperature above than 1000 Celsius. And only, let's say, vortex method that were talked already about, let's say, as a most used method in order to preparation of the suspension alloy particles. So the primary process used on an industrial scale to obtain metal matrix composite can be classified into two groups: the solid state, casting infiltration, and in situ processing. There are, of course, several advantages: better connection between matrix and reinforcement particle, better control the matrix structure, low cost of the processing, a wide base of the selection material. And you can see on the figure 8, the vortex method, and I think the elements are quite clear. And of course, we need inside, yeah, the melting furnace, a pellet, yeah, in order to mix well the particle. And of course, we need a drive motor, yeah, fixed on the console, rotating rod, sleeve bearing, and so on. If you go further to the mixing process of whiskers and aluminum powder, you can see here, let's say, some steps. And mixing process of whiskers and silicon carbide, you can see also here some steps. I mean, general steps without any other comments, yeah, for each step. And now let's go a little bit to the composite material reinforced with silicon carbide particles. Actually, it's our research. I will show you also the paper if you want to read all the results. It was published in Acta Physica Polonica journal, of course, also ISI journal. Let's see a little bit the content, the outline of the technology to obtain the composite material with silicon carbide particles. The first one, theoretical contribution regarding the gas to liquid and to liquid to solid transfer of the reinforcing particle. Going further to the experimental research of the characteristics of the composite material reinforced with silicon carbon particles. Experimental research afterward concerning the gas to liquid transfer of the reinforcing particle. The same experimental research, liquid to solid, yeah, and a little bit some experimental research concerning the tensile strengths, concerning the structural analysis, fracture surface analysis, distribution of silicon and carbide, and ultrasonic testing. That's all that we did. I mean, concerning that we done concerning the experimental research. Actually, was our research direction on national project. I think 6-7 years ago. So, as I mentioned before, we got an equipment, we got a patent in Romania, for the equipment to manufacture the particle reinforced composite material. You can see here the general sketch, yeah, of the equipment that we got the patent. Advantage, better homogenization and fast cooling. From our point of view, this is the main, let's say, advantage belongs to our equipment. Okay, and the technology steps are as follows: introduction of the silicon carbide particles into the aluminum liquid matrix, the stirring of the mixture, the heating of the entire mixture, the cooling of the entire mixture, the solidification phase of the mixture, and of course the extraction of the composite material. So if you will visit our university, our department, you will see that we have this equipment in my lab. It is working you can do, let's say, some experimental research. Okay, a little bit some theoretical contribution regarding the gas to liquid transfer of the reinforcing particles. We realized a new model starting from the following assumption, because it was not possible to have a new model with, let's say, some assumptions from this point of view. And the assumptions were as follows. During all stages of sinking, the thermodynamic equilibrium of the surface to the phase junction is applied. The second one, the specific interfacial energy is isotropic one. The gas to liquid metal interfaces is plain and free of oxides. The next one, the surrounding reinforcing particles do not interact with each other. The next one, the effects of the thermal gradient, the melt convection, and the chemical reaction to the liquid metal to particles interface are negligible to full immersion. And the last one, the reinforcing particle movement has been assimilated to the vertical plane, and please see here the figure number 1 on the distance of a rigid sphere with the radius. I think you can see here the R is the radius of the particle. So these are the 6, let's say, assumptions that we needed before starting to create the model. Okay. Against one rigid sphere will act the following forces. Force due to its weight, buoyancy force, and the force due to their interphase tension. Altogether, yeah, the buoyancy force and the force due to the interface tension can be calculated for some position where the center of the mass of the sphere has the z coordinator, okay, which means that the sphere has vertically lowered it on the z distance as shown on this figure. From this figure, you have to keep in your mind that the radius is rp, okay? We use also the critical speed, you will see later. And the resultant forces, and afterwards we done all the calculus and so on, yeah? The resultant forces that act on the particle during the immersion is the relation that we, let's say, we got. It's a lot of calculus, yeah, up to obtain this relation. Theoretically, Karl Park want to say something. Okay. And because this resultant force is conservative, the energy conservation law can be applied, isn't it? Yeah. And by their integration at z equal with diameter, I mean double radius, yeah, limit, we can obtain the critical velocity expression and incorporation at the gas to liquid transfer of the reinforcement particle. We put the main idea on the critical speed, okay, of the transfer, yeah, from where? From the gas to liquid, from the liquid to solid one. And you can see also the relation, yeah, for critical speed that we got. Theoretical contribution regarding the liquid to solid transfer of the reinforcement particle. So the mathematical modeling of the solidification flow imposes the following restriction. The reinforcing particle is spherical, as we talked 2 days ago, yeah? You saw that there are many shapes of the particle, but it's not possible to take into account, let's say, rounded one. Let's say you have to make the approximation hexagonal one, and so on. We have to make the approximation for the spherical one. The next one, The rejection force is given by the interfacial energy variation with the distance between the solidification front and particle. The third one, the balance corresponds to a distance between front and particle of 2 atomic diameters. The concentration gradient is negligible. The different thermal conductivity determines the curving of the interface. And the last restriction, the mass transfer is done only through convection. You can see that the force that acts against a spherical particle, here it's missing, the radius. So the force that acts against a spherical particles, I mean RP, okay, radius, and the density that moves with the critical speed, I mean VCR, okay, in the solidification front influence area, you can see as shown in the figure number 3. So the forces, the gravitational force, the buoyancy force, the Stokes force, and the rejection force given by the interfacial energy. So we got also the movement equation, yeah, for the critical speed of the solidification front, and horizontally is non-linear and cannot be integrated, but for the particular case, we can do it, but on the equilibrium, let's say, stage. In this case, we got the relation for the critical speed. And now a little bit information about the experimental results concerning the gas to liquid and liquid to solid transfer of the reinforcing particle. We used 3 types of alloys, yeah? The chemical composition, magnesium, copper, silicon, and so on, mangan, aluminum, the rest. Another one, the critical displacement rate of the silicon carbon particles for the penetration into the melt of the aluminum alloy. Yeah? You can see all the information, including the density, surface, contact angle, and the critical speed. So we made all the calculus for the critical speed, take into account the relation that we already presented. Also, you can see the radius, yeah, 2 levels, 20 and 60, yeah, for the particles. And the first results based on, let's say, variation of the critical speed of silicon carbide particles. You can see here two diagrams: critical speed and the radius, yeah, and which are the value in case this is the results. In case of first alloy that we used with 2 values for the particle radius. This is the results in case the second alloy that we used, and this is the results, I mean the variation between critical speed and the radius in case of third alloy that we used. So you can see that the biggest critical speed, I mean the speed for transfer to gas to liquid, yeah, is in case the third alloy that we used. We can go further to make the variation between critical speed and the density. Yeah? First metal used, the second alloy used, the third metal alloy used. Excuse me. So here it's a little bit, you can see, different. Here is the highest one, the third one, yeah, it's the second position. Yeah, and here the last position in case of values for critical speed. Now the critical speed of the solidification front. I put here the information, also take into account the critical speed values calculated, yeah, from liquid to solid. because now we are talking about the solidification front. And also, you can see the type of the particle, radius, interfacial tension difference, and look here about the variation, yeah, what happened with the smallest, let's say, radius, what happened on the highest radius of the particle. So we can talk about the highest speed, yeah, only in case of the small radius of the particle used. If you want to make, to going further, also the variation of critical speed is a function of density. Yeah, you can see also that the highest, yeah, is in case, let's say, of is in case of the density are, let's say, more or less the same in case of the first alloy that we used. The planning experiment, particle granulation, yeah, casting temperature that we used, mixing time, and percent of the particle. And a little bit results about the tensile strength. You can see the characteristics curve for the base alloy. Yeah, look here, it's around, let's say, 90 megapascal. Okay, and if you go further, yeah, in case of test number 4, you can see that it's more than 180 pascal. So more or less, it's double, okay, as value. Structural analysis. In case some structural analysis of the matrix alloy, first alloy here, second one, and some microphotos obtained for composite, also first alloy, second alloy. Of course, we've reinforced with the particle 20 micrometers for radius and 60 micrometers for radius. The main conclusion for the bigger particles, I mean 60 micrometers, some of the causes of the fragmentation during the fragmentation process are likely to be seen. Yeah? I mean relatively high temperature of strong shaking of the mixture of alloy reinforced with silicon carbide particles. You can see also, yeah, our paper that was published also in Metals and Materials International. Yeah, you can see over there that you will find all the results and all the details. Please.
One small query.
Yeah.
If you see, when compared to the base alloy, where you have dispersed things, and you can see that all the silicon carbide and rest of the particles are being agglomerated only at the grain boundaries, rather than within the grains.
Yeah.
So, any particular reason for that? Because why I ask this is because when we this is a cast aluminum product, yeah. So do you do stirring process while qualification or?
Here it's I have many micro photos, yeah, of the results.
Okay.
Yeah, it's about the mixing, yeah, process,
Okay.
yeah, inside of the enclosure, yeah, and maybe of course. I don't want to say that our equipment will have, let's say, 100%. Yeah, I mean the best result concerning the mixture, yeah, of the particles.
Okay, okay.
Yeah, and could be from time to time some agglomeration. Let's say. Maybe I put a wrong image.
No,
Dendritic structure
dendritic
also
structure also we can see. It's a very good structure.
Yeah.
10B.
For the first, yes,
10B
for the
is
first.
a very
Yeah,
good
very good one.
structure.
Yeah.
Very good one.
Yeah. The break images from surface, I mean breaking surface with the particle reinforced. You can see in case 20 micrometers, in case of 60 micrometers, brittle break of the composite and existence of the silicon carbide particles in the fracture zone. I put only one. You can see results, not many. Yeah, I put only one. And distribution of the silicon and carbide, you can see here. Yeah, which is the distribution? The red one is silicon, the green one is carbon one. So the weak distribution of the carbon can be observed, which confirms what? That during the processing, okay, the carbide, aluminum carbide, has been formed. This is quite important because why? Which improves the wetting process. Wettability. Wettability process. Okay? This is, let's say, the main conclusion from this point of view. And of course, ultrasonic testing. We made the ultrasonic testing also for the experiment number 4. And here could be observed the presence of some small, very slight discontinuities. I mean, maybe some porosities, okay? Which do not have a major influence on the subjective tensile specimen. Because from this reason, a very clear display on the end, HO, can be observed. Yeah, okay? So this is the ultrasonic testing, what happened with the, let's say, the whole structure, the whole thickness structure of the material. There are many, many results in here, but I put only a few.
One small query.
Please.
So in ultrasonic, we get the reflected sound.
Yeah.
So that is the third peak or second peak?
First peak.
First is on the left. So that is the reference peak.
This one.
Yeah.
This one.
Ah, yeah.
Yeah?
That one is the reference one.
Yeah,
That
yeah,
means
yeah,
the
yeah.
depth.
Yeah.
Okay. The second one is the.
Maybe over there for the second, for the third, you know, some
Okay.
bigger, you know, porosity and so on. Yeah. Met and was not possible, let's say, to have a.
If we see the first peak,
Yeah.
and the second and third one, it's diminishing, or maybe it represents maybe it have gone down, or the back wall has come again and
Could be.
hit the surface,
Could be.
something like that.
Could be something
But
like that.
we cannot tell it is porosity. Porosity means it will be still lower.
Because yeah, we put over there some porosity. Yeah, maybe, but could be another reasons, of course. Yeah.
But another thing I was noticing is doing ultrasonic testing in aluminum is very tough
Yeah.
because you need a reference sample and you should make sure the wave passes it perfectly.
But we had a rougher
You
sample.
had a reference sample?
Yes, of course,
Okay.
of course, of
Yeah,
course,
yeah.
of course, yeah. Because the
But
quality.
it's tough.
Yeah,
It's
yeah,
not
yeah.
easy.
Yeah, it's not easy, of course.
Easy like steel.
Yeah, of course, because you use aluminum. Yeah, of course.
Aluminum.
Yeah. Okay. I put some conclusion, but already, let's say, we already discussed. And I put here some information, I mean about the papers, the results of the papers that are used during the lecture that we published together with my colleagues on different journals. You can see polymers, Acta Technica, Nanoscience, Macromolecular Symposia, again polymers. You can see also Applied Science, International Journal of the Precision Engineering and Manufacturing. Was very good collaboration here with Professor Park from South Korea. Another one on Macromolecular Symposia. Materials, good collaboration with Professor Esteban Boisman, we publish in e-polymers. Materials, Indian Journal of Engineering and Material Sciences. Do you know this journal?
Yes.
Do you know? Yeah. Do you know Professor Benival?
Yeah, many one.
Yeah. Now he's on retired time. Yeah. Very good professor. Very good.
Some papers.
He attended our conference, I think once in Poland and once in Romania. Yeah. Yeah. Very good editor-in-chief of this journal, and I'm one of the editor of this journal. many years ago, he invited me to become editor. Journal of Tripology Transaction of the ASME, Material Research Express, very good journal, yeah, on UK. Composite Part B Engineering, yeah, you know that Composite Part B Engineering now is the highest journal with more than, it's more than 111 impact factor, I think, I'm afraid now, maybe bigger, yeah. Again, Indian Journal of Material and Sciences, Materiale Plastice, yeah, it's one Romanian ISI journal, yeah. Now the journal has 0.8 impact factor, yeah, good one, but you know, the topic is tight, yeah, only on plastic materials, biodegradable materials. I will invite you to join and to publish, because it's without APC, okay? So this is quite good. Composite Part B, another one, Metals and Materials International, Materials and Manufacturing Processes. Also, there are two important journals, Acta Physica Polonia, very good, yeah, and of course, again, Materiale Plastice, another journal. I put only a selection, yeah, of the publication that I used during my lectures here, yeah. Hopefully, I don't know what to say, because today in the morning, well, I was so surprised, yeah, to celebrate my birthday, yeah, and was you know, so nice for me, and I will not forget, yeah, this event. Yeah.
Same as
Yeah.
So one small,
Yeah, please.
just for academic interest, have you done any kind of acoustic emission testing in?
Not yet.
It's very tough.
Yeah, not yet.
So there is no kind of
No.
standard how to get it based on
Not
the
yet.
stress.
Not yet. Maybe we'll do it, but you know, this direction research, let's say, it was many years ago.
Because
We did not.
you have posted that ultrasonic. I would have.
Yeah, you're thinking about
because
yeah.
we for the previous lectures
Yeah.
there were a lot of polymers, plastics and all. One of the technique is you can't use ultrasonic in that. So that is why I just asked
Of course, no.
whether you have done
No.
acoustic emission. No.
No.
The equipment
Are you
cost is,
involved in acoustic emission?
No, I just want to know.
Ah, you
Because
just wanted to know.
We had an
Okay.
exposure,
Okay.
but
okay.
it is very tough.
Yeah.
It is.
It's difficult.
You should have a lot of sensors and all packs, and based on 3 sensors only you will be
Yeah.
able to get the signal.
Yeah.
But I just
Yeah.
asked whether you had a facility like that.
Okay. Cât o durat? Cât?
15 minutes.
Okay. So, this presentation was, let's say, short one, because really I didn't count the time, yeah, for each lecture, because I had no time to do it, yeah, and my, let's say, wish was only to transmit the main idea, yeah, because doesn't matter we're talking, let's say, 2 hours or maybe 1 hour. I think the message concerning the research direction that we want to send to you is the same, I think. Okay? I don't know what to say. I'd like to say thank you.
Thank you so much.
Thank you. Yeah.
Thank you.
And please contact me. Yeah.
Definitely.